Good afternoon, everybody. Let me introduce myself. My name is Han Dong. It's in the reverse order of this last name and things. And I worked for a Chinese company called ByteDance. It's doing some mobile apps development. I don't know if anybody of you use one of our products. It's called TikTok. Have anybody used that? It's a short video apps. Okay, let's just jump to today's topic. Today's topic is that we have development high performance IO manager based on libuv in our company, and we use it in some internal network applications. But it turned out it's performed quite good. So this is my experience report. It will be quite long, so I have to do it more quickly, I guess. So first, I have to present this schedule problem. If you haven't heard about it, the problem basically consists of these three parts. That modern OS works in units of thread. That you can do multiple works concurrently using multiple threads, right? The problem is that once one of the threads doing I/O operations, for example, it's trying to read a large file from the disk, it may stop itself from running. Now we want it stop its own, but it won't stop all the other threads. So this is basically how the problem is. In GHC case, this is not OS thread, it's the GHC lightweight thread. We want that one thread doing I/O won't stop others from doing work. Okay, so let me give a short introduction on the event-driven I/O. Okay, this is an API called ePool. It's present in Linux. Since which version I can't remember, but it's basically work like this way. First, you have to create an ePool file descriptor using this function. After you got your ePool file descriptor, you can add your real file descriptor, for example, the socket, to this ePool file descriptor with this function called ePool control. The control have several operations. For example, you can add, you can modify, you can delete. And you have to tell the kernel that what kind of event you are interested in. For example, you are interested in readability or writability. You use the different event types. There's ePool up, ePool in, something like that. And here is a definition of the event struct. After you add your normal file descriptors, now you can wait on the input file descriptor. Yeah, you cannot directly wait on the file descriptor. You have to wait on the first created input file descriptor. This function, ePool wait, will wait until there are events that happened on all the file descriptors you added to the input file descriptor, or the timeout is reached. So basically, these APIs can let you doing concurrently I/O with only one OS thread. Yeah, you don't have to start multiple threads to do multiple concurrently file reading or socket receiving. You can add multiple socket files to only one ePool file descriptor, and you wait on that. I have to explain more on this timeout parameter. You can set the timeout to 0. In that mode, this function will return immediately, no matter if you receive some events or not. So it's, you can take it as an event check. You just check on all the previously added files. If there is no event, it still returns immediately. Okay. So this is how ePool works. And okay, since the time is limited, I won't go through the Windows part because Windows have a slightly different model on this. But basically, the event loop thread model is quite similar. It works in this way. How to process concurrent I/O operations with only one OS thread? First, you have to prepare a set of interest file descriptors. For example, you open 50 sockets, and you are interested in all of the 50 sockets. Now you add all the sockets to for example, a equal-FD or the KQ-FD, something like that. After the weight returned, you can retrieve the events and loop to process all the events you receive. And during processing, you may modify the file, the set again. You can remove the file descriptor from equal file descriptor, or you can add root file descriptor, something like that. Then you go back to step 2. This is a loop. This is a so-called event loop model. This enable you to do concurrently IO operations with only one OS thread. Yeah. Okay, so this is just a quick review of the event-driven IO. Now I'll present to you the libuv library. Actually, it's quite rare to see it in academic papers. I searched for libuv as a keyword, but no paper come out. My paper may be the first one on the SM, so it's quite interesting. But this library is brilliant. Really, if you go through their source code, you will find that they handle a lot of very complicated. If you're doing event-driven IO on Mac OS, you know that you have to re-enable some events after you receive one. That's kind of very complicated. And the libuv supports the regular file. It's actually not supported by equal or KQ. The regular file means the file on the disk. It's not a socket, it's not a terminal, it's not a serial port. It's just a plain file on the disk. Why this is doing this way? Why people don't support the regular file? Because from the point of kernel, from the point of operating system, the regular file should be always ready. For example, if you're trying to read a file, the operating system should be prepared for you. The content should be lived in the page cache. If it's not, it's the fault of operating system. So operating system always recommend you to do regular file I/O using a synchronized API. But in practice, it's not performed that good. So libuv supports regular file via thread pool. It's start operating system threads pulled back in the background, and you can just submit your I/O operations as a job to it, and it will notify you once the I/O operation finishes. Okay, the last point is that libuv did a brilliant job on Windows. It unified the TTY API. If you do some programming on Windows, you want to change the color of the terminal, you want to print some Unicode code points, you will see that maybe some strange things come out because it didn't work in Unix way. It doesn't support the ANSI control code. But libuv supports this by translating the ANSI code you give to it, translate it into the Windows system call, so it works properly. So overall, libuv is a cross-platform event loop framework. Yeah, that's what I'm called. It's very good. If you are doing an IO framework from ground, from zero, you should really seriously consider about it. Let's see how does it do the asynchronous IO operations. Let's just use TCP as an example. Okay. The first function, the UV loop initialized. Here, this function is kind of like the equal create. It's creates a new event loop. This loop struct is a memory you allocate from whatever the malloc or other memory manager. It doesn't need to be done by libuv. You can just supply the memory location to it, and it will initialize the memory into a struct that contains the loops. Okay, now you have some sockets. You can use this function, TCP open. This socket parameter is the file descriptor in Unix and the sock type in Windows. You can make it into a UVTCP struct. This struct is something like a file descriptor, but with additional information. Now you use this function. You TCP initialize. This function is similar to the libuv control. It's like add your TCP, the socket, to the loop. Okay. And now we have also got this function, the UV run. This is the input wait. In that sense that you can call this function UV run, and you can wait this function finish. Then you know that some events has come. In fact, the UV run model supports 3 models, and it's a simplification of the timeout pattern. You can use the once mode. In that mode, it's just wait until there are events come. If there is no event, this function will block forever. And there is a no wait mode. That's just the timeout equals to 0, something like that. You just pass no wait here, and this function will return immediately, no matter if it got any events. And this default mode is designed specifically for Node.js, so we don't use it. And okay, so now we have to make the TCP as a stream interface. This is the libuv stream interface. This is related to the libuv's internal event masking framework. That means that even you have already added your socket to the loop, you still have to enable it explicitly. Let's see. Here, yeah. This API works like this. The UV stream struct is a parent class of the UV TCP struct. They basically share some field by the CTP macro techniques. So you can use this function on a TCP handle. And then you supply an allocation callback and a read callback. This callback will be called by libuv at the proper time. You don't have to concern when will this function get called. This function will get called when the data come. Yeah, the libuv will call this callbacks for you. The signature of these callbacks are this. Inside the callbacks, you can get your stream the handle back. This is the TCP handle, and you can get how many bytes you have read from the client. And this is a buffer struct. This struct have to be filled up in this allocation callback. Yeah, libuv never do a memory allocation for you, so you still have to do it yourself. And there is a function called UV read stop. That means it will turn off the event mask, and this TCP socket will never receive any events anymore. The write interface is quite similar. It's have to supply a write callback, but in addition to the parameter here, you have to supply another write struct. This is a special kind of struct called request. This struct can let you to do multiple writes at the same time. It means that you can call UV write a lot of times. Each one won't block the next one. And inside this write callback, you can get your request struct back. So you can pass some context between the write function call and the callback. Okay, so this is basically it. Now this is how we pass the context from the I/O operation to the callbacks. There's lots of data field in all this struct. It's quite unified in the libuv design. So okay. Now the problem is that how can we combine the GHC runtime system with this unit loop? The basically idea is like this. First, we have to give I/O call an identity. That once you want to do a read or do a write, I give it an identity, and we'll issue the registration. Then now we can skip. We can put the Haskell thread. This edge hyphen thread is just short for Haskell lightweight thread. It's just too long. So whenever you met this edge thread, it stands for Haskell lightweight thread. Okay. Now we have to find a proper time to do the waiting, to do the input wait of the UV run. Yeah. And after the run return, we can get the file, the ID back via the context parsing or something like that. Then we process the event inside the loop, and we can resume the previously sleeping Haskell lightweight thread. All right. So this is basically the idea how we can combine the runtime system with the event loop framework. Okay. So here is I still have time, but okay, that's really tough. In previous version that the JSC ship with called IO manager, to do it in this way, it use the file descriptor itself as the identity. Since the file descriptor on Unix is the least used integer, so it's quite a good key. And it stores STG callback inside the table. And after registration, it just blocks the thread by M-wars or the P-wars, and it will unlock this using the callbacks. And at what time the IO manager do the waiting? That's IO manager. The MIO starts IO manager thread alongside all the user thread on the same capabilities. For example, if you start Haskell code with runtime parameters with let's say 4 compatibilities, the IO manager will start 4 edge thread concurrently, each one on each capabilities. So that's one IO manager thread on one CPU core design, and after capabilities schedule loop finish, it's time for the IO manager thread to run. Okay. So now let's jump to see how do this STDIO do it. We cannot use file descriptor itself now because I want the code works on Windows, and on Windows the file descriptor doesn't have the least used integer property. So we use our own integer allocator. It's just a simple algorithm based on the stable pointer. It's quite short. Okay, now we tag the I/O operations with our own allocator keys, and the other logic, the waiting logic, is quite similar to the MIO's one. And we just skip the callback table design, and because the most time the callback is just a simple call to put M1, so we directly store the M1 inside a giant array. The array is indexed by the slot. Okay. Now on the libuv side, each time the callback is called, we have to record the slot and recover it in Haskell land. So let's see how we do this. Okay, we attach a small struct, here to the libuv loop struct. This struct, these two fields, the event counter and event queue, forms a small queue that once event happen, a callback happen, we can push a slot in this queue. And this two field, the buffer table and buffer size table, is used to passing the buffer parameters to libuv. And in Haskell side, we have also this data structure corresponding to this one, so that we can pick some data back and poke some parameter into the buffer table. Okay. So now this is the code that how we can pass in buffers. Just this function pick the buffer table's pointer, and this function poke the buffer into that table under the slot. Okay, so now we have to supply the callbacks. The callbacks is predefined. It's not supplied by user. It's predefined by the library, by me. So it's once libuv asks you to allocate memories, we can just get the slot number from the handles context, and we just use that data to get the buffer from the loops context. And the read callback is quite similar. It's let's get the slot from the handle of the context and push the slot to the loops context. Here we record the end read. This is the result to back to the buffer size table, because at this point the buffer size table's value has no use, so we can reduce this array. Okay, we can do all this stuff because the I/O operations basically is quite simple. It doesn't have too complex parameters or return values. Basically, it's all it's need. For example, read and write. All it's need is a buffer. You want to read to or write from, and the return value is basically how many bytes you read and how many bytes you can write. So all these things can work with only this four fields. Okay. So now let's see how Haskell side that the I/O manager thread is doing pulling things. The pulling is divided into two modes. Actually, here is a Boolean parameter. The Boolean parameter is called the block. That means if we want to do a zero-time check or if we want to do an infinity time waiting, this is important because at some situations we can optimize the speed of these two different models. For example, if we don't do block, if we go to this else branch, we can directly use UV run. This is done by an unsafe FFI call. It's not unsafe, so Haskell runtime won't start another OS thread. But if we want to go to the block branch, then we have to check if the runtime system supports the truly concurrently safe FFI call. If it does, we just use the safe one. If it doesn't, we start a UV timer. This will limit the pulling time to the timer's timeout. Right? Here we choose 2 milliseconds. This branch is only reached on a single thread runtime system, so it's not quite useful in practice. But anyway, we have to deal with this. After the UV run finished, now the callbacks are already called. These callbacks are called during UV run by UV. So now we can pick the ping back. We can guess how many events we see, and each event have its slot number. And after we got slot number, we can pick the MVAR back and fill the MVAR with the result. Okay. So this is how the whole thing is work together. That we pass parameters to libuv and let libuv do the pulling to the callbacks, and we fetch process the event back to Haskell again. Okay. This is a reading example. This is how the library authors can do some bindings on libuv's API. For example, we want to read from a socket. This UV string type is just a struct that bundle the handle and the slot we allocate. So now we first get which MR we want to block. Then we clean up the MR first. Then we poke the buffer. We prepare here buffer and then these two parameters to the buffer table, and we call UV restart. This is corresponding to the UV's UV restart. Now this function will block the Haskell thread calling this read input until that the I/O manager fill this MR up, and this function will resume. And now we can pick the result back again. Okay. So the right. Oh, I have removed the right example because it's very similar. Okay, so there's one problem that libuv is not straight back. It's how to express this? It's actually, if you use epool, it's a multiple thread safe API. You can wait thread A on epool wait and add more events to the same epool and file this on the thread B, and you can still get all notifications. But you cannot do this in libuv because in libuv it maintains some internal state. So if you do that, you will mess up with its internal state and you cannot cannot get your notification, and worse, you may crash it down. So you have to find a way to make the event registration in sequence. So how do do that? libuv provides a mechanism that you can break a loop that's waiting. It means that if you have an event loop that's waiting in the UV run function, and you call a UV async send this function will break the loop. It will wake up. And the condition is that you add an async handler to the loop. Okay. So this is a very useful mechanism, and we use that to implement our UV manager function. This function will protect from concurrently registered traditions and pooling. There are two solutions. The first one is based on the soft transaction memories. I have defined the state, it's called lock, pooling, and free, while only the functions can only mutate the libuv state if the state is free. This is done by this. We enter a transaction now, we read the manager state. If the state is free, we just switch it to lock. We first lock it up, and then we do the things that the user wants me to do. If it's still pulling, then we call the async send to wake the loop up. And if it's locked, it means that there are other threads that trying to register the event. So we just try here, try here. Okay, this is a STM version, and there is also. Oh, okay. So it seems it's just too long. This is a version based on the optimistic logging techniques using M1. In practice, we choose this way because the STM version performs not so well. So let's see if the benchmark result. Okay, this is something I must show you. We have to set up a small benchmark that talks in HTTP protocol, and we use the WARP benchmark tools. The detailed figures presented in the papers. Here is the curves. You can see that the performance is better than the previously one, and maybe not that large, but slightly better. It's 10% on the high potential level. Yeah. I forgot to introduce that. This benchmark is written with different runtime system. For example, this is Golang version, this is Node.js version. This is the Haskell, the MIO version, and this is my version. Okay. So all the details, all the setups are in the papers. If you are interested, you can check it out. This figure is just a record throughput. It doesn't count the latency and the timeouts. In fact, this new I/O manager improved the latency and the stability a lot. And here, at this very high complexity level, there are lots of timeouts with MIO, but with this one, there are seldom timeouts. So it's indeed works better. Okay, so in the future, I have to make all the libuv API with Haskell bindings so that the other developers can use it easily. And I'd like to bundle the transaction layer secure. Yeah, this is very important for HTTP framework. And I'd like to do some works improving the packet data structures for the tags. That's it. That's basically what I have to do. Okay. Now, thank you. This is the code on this.
Yeah, so we added this thing recently so that you can put an envar from C. There's an API in the runtime system to put an envar directly from C. I think that would make your thing simpler, wouldn't it? Because you can.
You mean that the HS put envar function?
Yes.
Yeah, I had one section on this previously talk, but due to time limit, I can't present the result to you. The fact is that if I use the HS put try put envar, you see it's quite slower. Yeah, it's slower. I guess it has to do with stable pointers overhead. Because the current stable boundary table is it's allocated with giant log globally. It's not done per capability. And when you call HS try to add more, you actually call malloc once. Do you remember that code? I read that code. You malloc a small struct as a message to attach to the runtime system's compatibility struct. So that is not really good from the memory management viewpoint. Because if you frequently allocate small struct with malloc, it will bring some fragment to the memory. So I guess it may have some problem with that. Yeah.
Okay, thanks.
We can talk it later if you want to know more about the experiment. Yeah.
Should we have one more question?
Yeah, I have one more.
Yeah.
So do you have a sort of longer term goal of would you eventually see this possibly becoming, like replacing the existing IO manager in GHC, or do you see this as something that continues to exist as a
that depends. Currently, it just stay as our company's internal project. We use it in some our own code, some RPC coding framework. But once I have done all the stuffs I described here, I mean the transaction layer secure and the text. Once I get every stuff packed up, I probably will release it on the package. And depending on the community's reaction, I think that it's okay to bundle with Jet3 or not. But personally, I don't think that's a good idea because a separate package is more lightweight, I think. If we put these things to the runtime system, it will make some change become harder. Yeah.
Thank you very much.